Hello everyone, today I'm going to show you how to use the moving mesh method to simulate a ventricle in ANSYS Fluent. For that we have provided a project file in the repository where you can either use the given geometries for the ventricle or use your own. If you have UCD data, then you should use the provided MATLAB script to convert them to STL. If you have your STL files, you can put them in this. This is our project example. You have to put them in basic setup files, dp0, fff, fluent, in the STL folder. You can exchange them for yours, but keep in mind to keep this naming system consistent. So starting with ventricle 0 and then iterating. So I will go back into the original path of our project. Now we can open this project by either double-clicking or dragging it into Workbench, or opening it in Workbench directly. And the first step now is to import the geometry files, which we can do by either right-clicking or edit geometry in SpaceClaim, or by double-clicking in my case, which will open SpaceClaim. To import the geometry in SpaceClaim, you can go to Assembly, File, and we are already here in the STL file that we just put our geometries inside. So we go show all files, and before loading our first time step, we check if the options are correct. So in options, go into file options and then STL and check if the import units are the one you want to use. Sometimes with automatic, it can cause problems with the scaling. So I suggest always use your dimensions that you want to use. So we want to import the initial time step, and in that we have our geometry here. We did some modifications to this STL, so that's why it says exported from Blender. And we can then do this conversion to a solid without merging phases, which is important to create our solid. And this we can then close SpaceClaim, and then we can, in Workbench, we can then update upstream components. And when we then open meshing, either edit or double click, we are asked if we want to read upstream data, and we would definitely want to do that. So we click yes, which will start meshing. In meshing, we have to modify some of the setup settings. So first of all, we are using a patch conforming method, and we have to select a geometry for that. So we go into the body selection in meshing, and we select the whole body and apply geometry. And the same we have to do for the three named selections. If these selections are missing in your case, you can always insert a new named selection. And then apply the coming geometry definitions that I'm going to show you. So for ventricle, we are going to choose the whole body again, as we did in patch conforming method. So whole body again, geometry, and then apply. For the inlet, we only want the inlet faces. In this case, this is the mitral valve, and we only want to select the inner part of the mitral valve, the part that I'm selecting right now is the annulus of the mitral valve, so we do not want to select these faces. So I'm going to do a little trick, and I will hide all of the annulus faces by pressing F8. So after hiding these faces that were connecting the mitral valve to the rest of the ventricle, we can double click while we are in the face selection screen. And then on inlet, we can select these faces as the inlet. We can then do the same for the aortic valve. If you hold control, you can easily fix one of these mistakes. And then you can hold your mouse while holding control to select all these faces. And then you can press F8 again to only select the faces, to hide the faces, and then only select the inner part of the geometry. Then if you want to revert the the hidden faces, then you can just show all hidden faces and then you're back to your whole geometry. In the meshing, there might need to be some adjustments in the element size depending on the size of your STL. For our case, I'm just going to go with 1e to the power minus 3. And then we can already mesh. So this we can either do by generating mesh here or here. After generating the mesh, you can observe your mesh with the mesh metrics. You can click, for example, these very relatively skewed cells to maybe introduce some face sizing at some points, which we're not going to do in this tutorial. Just click here, you're going to see your whole mesh again. And to see your inside mesh, you can use section planes, which you can create here. I will create this section plane along these two heart valves, and then we can see the inside of the mesh, which for our case looks good. So now that we have created our mesh, we can then close the meshing process. And then we can update our workbench file. So we wait for meshing to close. And now we can click on setup, right click, and update upstream components again. So it will then update the meshing, and in the next step we can start the setup. It's going to take a... Now that the mesh has been updated, we can right click setup, or just double click the setup. So now we want to reload the upstream mesh, so we click yes. And this will start Fluent. Before Fluent is going to start, we have to tell Fluent that we want to use double precision, and that we also, in our case, we want to use four cores, 4 nodes. So we just going to do 4, but if you want to use more, then you have to change it here. In Fluent, the first thing you want to do is go into parameters and customization and update the number of nodes you're using, number of user-defined node memory locations, to the number you put in for the number of nodes you're going to use. And then you will go into user-defined functions, compiled, and then you will add these 3 C files. Use the built-in compiler and build. Yes, you want to proceed. after compiling, you can then load your compiled documents, and then you can assign your mesh to the STLs by using the execute on demand. First assign ID libudf, and then execute. This will then show you how many nodes are for each core, for each node. And then you will run 2 Python scripts. So you're going to open an IDE like I'm using Spider, for example. And I'm here in my work directory with my project file. So I will go into the Fluent location, and then I will open ps_det endpoints. Don't mind this, it's not supposed to be there. So now we want to run this script. And it's going to ask you if we want to generate a correlation file, which we want. And then we have to give the reference frame ID, which is always going to be the initial ID. So the ID of your first STL file, which is ventricle 0. So the input we're going to use is 0. And this output we can already copy because we need it later to adjust our another function. But for now, we will let this run. Next, the function is going to ask for the start frame ID. In our case, again, it's 0. We can type in 0, enter, and the end frame ID is the last STL we have. So for us, it's 12. And then he's gonna create the PTS folder here. Next up, we can run the ps_int endpoints script, where we have to give the total number of frames in a cycle. In our case, we have a total of 13 STLs because we have 1 to 12 and also 0. So we have to type in 13. And now we have to give the amount of the amount of intermediate frames for the interpolation. Usually in this case I would go for something like 20, but for demonstration purposes and for speed I will go to 10. And now we can choose a interpolation scheme, and we're going to use the monotonic cubic spline scheme. So this will now create this folder here with UDF PTS, which are the surface files which are going to be used during the simulation, where the user-defined function will load these surface files after a certain amount of after every time step. So now the next thing after this is run. We want to do is we want to update the UDF execute dynamic mesh. So you can double click on that and open this. And there's 2 things we actually want to update. First is the number of time steps, and the second is the number of points. And both of these information we can extract looking in the console. So the total number of frames after interpolation is 131. So we're going to copy that and paste it into the number of time steps. And if we scroll a little up, we have the total number of nodes on the surface, which is also the same as all points number. which is 15,418, and we can copy that into all points number. Then we can save, execute dynamic mesh using Control S or just save. And then we have to go into Fluent and have to unload the library that we used before. So we're going to unload, go into the Fluent folder and delete this compiled library. And now we want to recompile the new UDF execute dynamic mesh. So I have to first remove the old ones that are still saved here. And as you can see, we just recently changed this. So we're going to load in the new library and we're going to build that. Yes. After building, we can then load this UDF, this UDF, and then we can execute load mesh, which will then load, in our case, the first time step. And then we are almost ready to go. We can then do our simulation setups. So for our case, we have number of time steps, which is, as we were already seeing here, which is 131. So together with the initial frame, so it's just 130. So we're going to do 130 per cardiac cycle. In our case, the RR duration, or the duration of the cardiac cycle, is 0.557 seconds. And so we have to find the time step size. We have to divide that by the number of time steps, so by 130. So it's 0.004 284 seconds. And you can also increase the number of iterations per time steps. Maybe if for our time step size, maybe 20 is a little too low, so we go maybe to 30 iterations per time step. You should also check if the boundary conditions are correct for the initial setup. We want to, so in the initial state, we want to start with the diastole. So in our case, there's our boundary conditions have only a pressure inlet, and the outlet is modeled as a wall, which will then be changed in the dynamic mesh settings. So we have some dynamic mesh events where we exchange the settings of the between the systole and the diastole. So the duration of the diastole for our case is 0.31892 seconds. And there we have, for each change between diastole and systole, we have 3 conditions that we have to change. So first we have to change the zone type of the inlet. We also have to change the zone type of the outlet, and then we are giving the outlet a pressure profile. The same is then be done. So this was a switch from diastole to systole, but from the other switch from systole to diastole at the RR duration, or the cardiac cycle duration, is then done in an analogous manner. So we changed the types of the outlet here to a wall again. Then we changed the inlet to a pressure condition, and then we define the pressure conditions. Since we have 3 cycles in this example, we have 15 time steps, 15 number of events. So we don't change back to the initial state. If we would do that, we had 18 number of events. So this is why we only have 15. So 3 for each change between systole or diastole. And we use smoothing-based dynamic remeshing with a diffusion. And when we go to advanced, we can make some changes to our setup. For example, we can use diffusion coefficient of 0.6 and 50 iterations with one of these stabilization methods. GMRS is usually the most robust, but it also takes a bit more time. But I'm gonna just keep it as is. This has to be adjusted for your simulation. This might have to be adjusted for your simulation, I have to say. So just press OK, and so we're done here. And now we basically just have to initialize the simulation. So we go into initialize. We're using hybrid initialization. Just initialize OK. Then we can load the mesh. So when this is the first UDF surface, this is good. If this is not the first surface, then you're not in the first time step in the initial state. And then we can initialize again. Okay, and then we can go into the simulation and run the simulation. If you want to do multiple cycles, you can just multiply this number by, for example, if you want to do 2 cycles, you can do just 260, or with 3 cycles, 390. In this setup, you can do 3 cycles, but if you want to do, for example, 4 setups, which would be 520, you would have to also introduce new dynamic mesh events, similarly to those that are already present. But let's just do, for now, let's just do 1 cycle in this simulation, and then if we calculate, we start the simulation. So that's basically it. Now the simulation is running smoothly. You can check on your simulation in the scaled residuals, and later on there's also some other plots that are some report definitions that are going to be plotted in the graphics department after 30 iterations of this time steps are run. Currently we are on iteration 12. And we have these values for the residuals, which we can then here see that at least this first time step is definitely converging, which looks very good. And now the server is going to slowly plot all of the report definitions that we are using. So for example, we can here see the average wall shear stress in the ventricular walls, total pressure, the volume of the ventricle, but you can also introduce your own report definitions and plot them. So yeah, that was a short introduction into the moving mesh setup with ANSYS Fluent. I hope this video was helpful, and have a nice day.